Hello, in this lecture we will answer on two questions. In the first question we will find out the area of this semicircle that is inscribed by the quarter circle, and in the second question we will find out the size of this angle theta of the right triangle ABC. So we'll start with the first question. In the drawing we have this semicircle that is inscribed by a quarter circle. We know that the radius of this quarter circle is equal to 3 units, and we want to find out the area of the semicircle that is inscribed by the quarter circle. So we'll start with the first method. In the first method we will define the center of this semicircle as point O, and in the next step I will present to you a new rule, that is rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So I will read rule number 1 again. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we also have the tangent AB here, this tangent AB is tangent to this circle at this point M. Point M is the point of tendency, of tangent AB with this circle, and the center of this circle is at point O, and OM is the radius of this circle. So here the radius OM, it is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Here, as I already said, OM is the radius of this circle. That is to say, we define it as R, radius of the circle, and because of the fact that the radius OM is drawn to the point of tendency, then the tangent will be perpendicular to that radius. Tangent AB will be perpendicular to the radius MO. AB is perpendicular to MO, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So we can implement rule number 1 in our drawing. Here, first of all, we will define this point as point A. We define this point as point B. This point will be defined as point C. We define this point as point D. This point will be defined as point F, as point E. This point will be defined as point F, and this point will be defined as point G. Here we will connect points O and B together by a straight line. Line segment OB is the radius of the semicircle. Why? Because it starts from the center of the semicircle, that is to say from point O, and ends at point B, that is a point of the semicircle itself, and this is exactly the definition of a radius. So OB is the radius of the semicircle, therefore we will define it, the radius of the semicircle as R, therefore OB will be equal to R. So here the radius OB of this semicircle, it is drawn to the point of tendency, that is to say, it is drawn to point B, that is the point of tendency of tangent AC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. That is to say, tangent AC will be perpendicular to the radius BO. So AC is perpendicular to BO, that is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? Likewise, we'll join points O and D together by a straight line. Again, OD is the radius of the semicircle. Why? Because it starts from the center of the semicircle, and that's at point D, that is the point of the semicircle itself. And this is exactly the definition of a radius. So OD equals to R, radius of the semicircle. And again, we have the radius OD. It is drawn to the point of tendency, that is to say, it is drawn to point D, that is the point of tendency of tangent CE with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to this radius. Again, tangent CE will be perpendicular to the radius DO. So CE is perpendicular to DO, that is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Okay? Here, because of the fact that ACE is a quarter circle, C must be the center of the quarter circle, and angle ACE must be equal to 90 degrees. Okay? Angle ACE must be equal to 90 degrees because we are talking here on a quarter circle. So inside quadrilateral BOCD, we have one two free right angles. I repeat again, inside quadrilateral BOCD, we have three right angles. The sum of three right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually this angle, angle BOD. In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here we will subtract 270 degrees from this equation, and we will get that the missing angle, angle BOD, is equal to 360 degrees minus 270 degrees, it is equal to 90 degrees. So we found out that the missing angle, angle BOD, this angle is a right angle, it is equal to 90 degrees. So actually in quadrilateral BOCD, we have four right angles, and any quadrilateral that has four right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral BOCD as a rectangle. I will write it down. So quadrilateral BOCD is a rectangle because of the fact that it has four right angles. Okay, quadrilateral BOCD is a rectangle. And we also have rule number 2. According to rule number 2, the opposite sides of a rectangle are equal to each other. I will repeat on rule number 2 again. According to rule number 2, the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of a rectangle BOCD are equal to each other. It means that BO equals to CD. According to rule number 2, BO equals to CD. According to the rule that the opposite sides of a rectangle are equal to each other, we will get that BO equals to CD. But BO equals to R. We already found out that BO equals to R. So from this equation, R equals to BO equals to CD, we will derive that CD is also equals to R. Okay? Here CD is also equals to R. This is the radius of the semicircle. Likewise, OD must be equal to BC according to rule number 2. OD must be equal to BC according to rule number 2, that the opposite sides of a rectangle are equal to each other. But OD equals to R. According to what we have already found out, OD equals to R. And from this equation, R equals to OD equals to BC, we will derive that BC is also equals to R. BC equals to R. Here BC equals to R, according to rule number 2, of course. So actually we found out that quadrilateral BOCD has 4 equal sides and 4 equal angles. Therefore, quadrilateral BOCD is not a rectangle but a square. So we can write down that quadrilateral BOCD is a square. Okay. Here we join together points O and C by a straight line. And in order to find out the length of line segment OC, that is the diagonal of square BOCD, we will implement the Pythagoras theorem on the right green triangle, triangle COD. On the right green triangle, triangle COD, according to the Pythagoras theorem, here PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, we get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CO square equals to OD square plus CD square. OD square plus CD square. So CD square or CO square is equals to OD square. OD equals to R, so OD square is R square plus CD square. CD equals to R, so CD square is R square. So in conclusion, we found out that CO square equals to R plus R, that is 2R square. Here we'll take a root out of this equation and we get that CO, the diagonal CO equals to square root of 2 times R units, okay? So I'll write it down that the diagonal of the square CO equals to square root of 2 times R square units. So in the next step, we will extend the diagonal CO until it touches the quarter circle in this point, point S. Point S is the touching point of the extended diagonal CO and the circle, and the quarter circle. And in the next step, we'll calculate the length of the small segment line of OS. So what is the length of segment line OS? It is very easy to see from the drawing that the length of line segment OS or SO, it is equals to SC minus OC. I'll repeat again, SC minus OC equals to SO. Okay, here, SC minus OC equals to SO or OS, it is the same. So SO equals to SC. What is the length of line segment SC? C is the center of the quarter circle. I will write here that point C is the center of the quarter circle. Point C is the center of the quarter circle, and point S is the point of the quarter circle itself. And this is exactly the definition of a radius. That is to say, CS is the radius of the quarter circle. And it is given as the question that the radius of the quarter circle equals to 3 units. So CS or SC equals to 3 units as the radius of the quarter circle. It is equal to 3 units minus OC. We already found out that the diagonal OC of the square equals to square root of 2 times R. So in conclusion, we found out that the length of the small line segment SO, it is equals to 3 minus square root of 2R. Okay? Here, OS equals to 3 minus square root of 2 times R. Okay, so in the next step we will complete the quarter circle to a circle. So we completed the quarter circle to a circle, and then we will extend diagonal OC by a straight line until it touches the circle. And we will define the touching point of the extended diagonal CO with the circle as point M. What is the length of line segment MC or CM? C is the center of the quarter circle, and it is also the center of the circle. M is the point of the circle itself. And this is exactly the definition of a radius. Any segment line that starts from the center of the circle and ends at any point on the circle itself is defined as a radius. So this is the radius of the quarter circle and also the radius of the circle itself. That is to say, MC or CM equals to 3 units. Okay? So in the next step, I will present to you a new rule. That is actually rule number 3. According to rule number 3, if chord AB intersects with chord CD at point O, then the following formula is true, that AO times OB is equal to CO times OD. So here we have chord AB. This is chord AB inside the circle, of course. That intersects with chord CD. This is chord CD. And the intersection point between those two chords is at this point, point O. Again, point O is the intersection point of chord AB with chord CD. Then, if this is what we have, then according to rule number 3, it is true to say that AO times OB equals to CO times OD. Okay, this is rule number 3. So we actually can implement rule number 3 in our drawing, because in our drawing we have chord SM intersects with chord GF at point O. Point O is the intersection point of chord SM with chord GF. Okay, therefore, according to rule number 3, we will get that MO times OS equals to GO times OF. And repeat again. Chord SM intersects with chord GF at point O. Point O is the intersection point of those two chords. Therefore, according to rule number 3, we will get that MO times OS equals to GO times OF. Here, what is the length of line segment GO? O is the center of the semicircle. G is the point on the semicircle itself. And this is exactly the definition of a radius. That is to say, GO is the radius of the semicircle. That is to say, it is equal to R. For the same reason, OF will be the radius of the semicircle, that is equal to R. Here it starts from the center of the semicircle, that is to say from point O, and ends at point F, that is the point on the semicircle itself. Therefore, it is the radius of this semicircle that is equal to R. So, what is the length of line segment MO? Here you can see from the drawing that MO equals to MC plus CO. Again, MO equals to MC plus CO. OS equals to 3 minus square root of 2R. and it is equal to GO, GO equals to R, times OF, that is also equals to R. So in conclusion, we found out that MC plus CO times 3 minus square root of 2R equals to R times R, that is actually R squared. We already found out that MC equals to 3 and CO equals to square root of 2 times R. And it is times 3 minus square root of 2R, that is equals to R squared. So here we have this expression 3 plus 2R times 3 plus square root of 2R times 3 times minus square root of 2R. This expression is very similar to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. That is to say, this expression equals to A squared minus B squared. And here, in our specific expression, A equals to 3 and B equals to square root of 2 times R. So, as I already said, this expression equals to A squared minus B squared. So A squared, it is equals to 3 squared, that is 9, minus B squared. B squared is square root of 2R squared. Square root of 2R squared is square root of 2, that is 2, times R squared. So in conclusion, we found out that the value of this expression, it is equals to 9 minus 2R squared, and it is equal also to R squared. In conclusion, we actually found out that 9 minus 2R squared equals to R squared. Here we relate 2R squared to this equation, and we get that 9 equals to 2R squared plus R squared is 3R squared. So 9 equals to 3R squared. Here we will divide this equation by 3, and we get that 3R squared over 3 is R squared, and 9 over 3 is 3. So in conclusion, we found out that R squared equals to 3. What is the area of the semicircle? The area of the semicircle equals to the area of a circle that is pi R squared over 2. So the area of the semicircle equals to pi R squared over 2. So that is to say it is equals to pi, and R squared equals to 3. So we'll substitute R squared in this equation by 3 over 2. So in conclusion, we found out that the area of the semicircle equals to 3 pi over 2 square units, or in terms of numbers, it is equals to 4.71 square units. Okay? I'll repeat again. We found out that the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equals to 4.71 square units. So in the next step, I will present to you the second method to find out the area of the semicircle. In the second method, we'll use the things that we have already found out in the first method. So here, we know that point O is the center of the semicircle. This is point A, this is point B, this is point C, that is the center of the quarter circle. This is point D, this is point E, this is point F, and this is point G. We have already found out that OBCD is a square. And the diagonal OC of this square is equal to square root of 2 r units in its length, and the sides of the square, they are equal to r. We already found out that GO is also the radius of the semicircle, that is to say it is equal to r, and OF, it is also the radius of the semicircle, that is equal to r. So in the next step, we will join point C and F together by a straight line. What is the length of line segment CF? C is the center of the quarter circle. F is the point of the quarter circle itself. And this is exactly the definition of radius. Any line segment that starts from the center of a quarter circle or a circle and ends on the quarter circle itself must be equal to the radius of the quarter circle, that is to say CF equals to the radius of the quarter circle, that is 3 units. Likewise, we will join point C and G together by a straight line. For the same reason, line segment CG will be the radius of this quarter circle, that is to say it will be equal to 3 units. Again, it starts from the center of the quarter circle at point C and ends at point G, that is a point on the quarter circle itself. Therefore, it is the radius of the quarter circle, that is to say it is equal to 3 units. So we have here an isosceles triangle. Triangle GCF is an isosceles triangle because of the fact that side GC equals to side CF equals to 3 units. So I will copy the isosceles triangle in a new page, and we will analyze the isosceles triangle GCF. Okay, so we have the isosceles triangle CGF or GCF. So this is the isosceles triangle CGF that I copied from the original drawing. Here we know that CF equals to CG. Those are the two sides that are equal to each other. Therefore, FG must be the base of the isosceles triangle CFG. So this is the base of the triangle. I write down that triangle CFG is an isosceles triangle. CO is not only the diagonal of the square, but it is also the median to the base GF. Why CO is the median to the base? Because so CO is the median to the base, median. So why it is the median to the base? Because of the fact that it divides the base FG into two equal parts, R and R. Okay? And we have rule number 4 that is related to the median to the base in an isosceles triangle. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So I will read rule number 4 again. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So according to rule number 4, the median CO to the base FG in an isosceles triangle CFG is perpendicular to the base. That is to say, CO is perpendicular to CG. CO is perpendicular to FG. So CO is perpendicular to FG. That is to say, this angle is equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 4. Why? Because the median CO is perpendicular to the base FG. So if CO is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle must be also equal to 90 degrees according to rule number 4. Okay? So, here in the original drawing we have the median CO that is perpendicular to the base GF. It means that this angle equals to 90 degrees, and this angle will be also equals to 90 degrees. Okay, so in the next step we will focus on the right triangle, triangle COG. It doesn't matter at all which right triangle we will choose, because they are identical. Triangle CFO is congruent to triangle COG. Okay? So we'll choose the right triangle COG, and we will implement the Pythagoras theorem on the right green triangle, triangle COG. So I'll copy the right triangle COG in a new page, and we'll implement the Pythagoras theorem on this right triangle. So we have triangle COG. So this is the right green triangle, triangle COG that I copied from the original drawing. So we will implement the Pythagoras theorem on this right triangle, triangle COG. By PT, the abbreviation for Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CG square equals to CO square plus OG square. CG equals to 3, so CG square is 3 squared, that is 9, and it is equal to CO square. CO equals to square root of 2R. So CO square will be equal to square root of 2R square. Square root of 2 is 2 times R square. So square root of 2R square, in conclusion, it is equal to 2R square plus OG square. OG equals to R, so OG square will be equal to R square. So in conclusion, we found out that 9 equals to 2R square plus R square, that is 3R square. We will divide this equation by 3 and we will get that R square, 3R square over 3 is R square, and R square equals to 9 over 3, that is 3. So we found out that R square equals to 3. R square equals to 3, but the area of the semicircle, it is equals to pi R square over 2. So it is equals to pi, and R square is 3 over 2. In conclusion, the area of the semicircle equals to 3 pi over 2 square units, or in terms of numbers, it is equals to 3.71 square units. Okay? I'll repeat again. The area of the semicircle according to the second method equals to either 3 pi over 2 square units, or in terms of numbers, it is equals to 4.71 square units. So in the next, we finish with the first question. In the next step, I will present to you the second question and two different methods to solve the second question. So here we have the right triangle ABC. We know that side BC of the right triangle ABC equals to 6 units. Line segment DE equals to 2 units, and line segment DE is perpendicular to the hypotenuse AC, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. In addition, we also know that AE equals to EC. Angle ABC equals to 90 degrees, and we want to find out the size of this angle theta, that is actually angle BAC. We'll start with the first method. In the first method, we will make a construction from point E. We will draw perpendicular on BC. Again, from point E, we will draw perpendicular on BC. So this angle equals to 90 degrees. And this angle will be also equal to 90 degrees according to our construction. And we will define the touching point of the perpendicular from point E and BC is point F. in the next step, we'll define angle ACB as alpha. But because of the fact that triangle ABC is a right triangle, this angle equals to 90 degrees. This angle equals to theta. So the third angle, this angle, must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle ABC to 180 degrees. This angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. For that reason, this angle must be also equal to 90 degrees minus theta. So here we can derive from it that alpha equals to 90 degrees minus theta, because this angle equals also to alpha according to our definition. Therefore, alpha equals to 90 degrees minus theta. Here we will add theta to this equation and we'll subtract alpha, and we'll get that angle theta equals to 90 degrees minus alpha. Okay, and if this angle equals to alpha, we will focus on the right triangle EFC. This angle equals to 90 degrees. This angle equals to alpha, so this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in this right small triangle EFC, 280 degrees. This angle must be equal to 90 degrees minus alpha. But here we know that 90 degrees minus alpha equals to theta. So we can write down that 90 degrees minus alpha equals to theta. According to this equation, it is true to say that 90 degrees minus alpha equals to theta. And what is the size of this angle? Angle DEF. Actually, angle DEF will be equal to the big angle, angle DEC, minus angle FEC. Again, angle DEC, the big angle, minus angle FEC, will be equal to this angle, angle DEF. So I write it down. Angle DEF, the missing angle, will be equal to the big angle, angle DEC, minus this angle that is actually angle FEC. I will repeat again, angle DF equals to angle DEC minus angle FEC. Okay, so angle DF, the missing angle, is equal to angle DEC. Angle DEC equals to 90 degrees according to what is given us the question. So we substitute angle DEC by 90 degrees. And we have already found out that this angle, angle FEC, equals to 90 degrees minus alpha. Okay, it is equals to 90 degrees minus alpha. So here we will open the brackets and we will get that the missing angle, angle DEF, equals to 90 degrees minus 90 degrees is 0. And here we have minus and minus is plus, so it is plus alpha. So in conclusion, we found out that the missing angle, angle DEF, equals to alpha. So this angle equals to alpha. So in the right triangle, triangle DEF, this right triangle if this angle equals to 90 degrees, this angle equals to alpha, this angle must be equal to 90 degrees minus alpha. But because of the fact that 90 degrees minus alpha equals to theta, we can substitute this angle that is equal to 90 degrees minus alpha by theta. We'll do it now and we'll get that this angle equals to theta. In the next step, we will prove that the right triangle ABC is similar to the small right triangle, triangle APC. But before that, we will define side DF as X, we will define side EF as Y, we will define AE, line segment AE as A, and if line segment AE equals to A, because of the fact that AE equals to EC, we will get that EC must also equals to A, must be also equal to A. So we will prove that the big right triangle ABC is similar to the small right triangle, triangle APC, this right triangle. So why those two right triangles are similar to each other? First of all, we know that those two angles, they are equal to each other, they are both equal to 90 degrees. So actually angle ABC of triangle ABC is equal to this angle that is angle EFC, and both angles are equal to 90 degrees. I'll repeat again, angle ABC equals to angle EFC, and both angles are equal to 90 degrees. In addition, those two angles, they are equal to each other. Why? Because they are both equal to theta. Okay? They are both equal to theta, therefore they are equal to each other. So angle BAC of triangle ABC is equal to angle FEC of triangle EFC, and both angles are equal to theta. I'll repeat again. Angle BAC equals to angle FEC, they are both equal to theta. Finally, this angle is a common angle, it belongs to both triangles. It is very easy to see from the drawing that this angle is one angle of the big right triangle ABC, but this angle, it is also one angle of the small right triangle, triangle FEC. Okay, so we can write down that angle BCA of the right triangle ABC is equals to angle FCE of the right triangle EFC, and it is equal to alpha, so it is a common angle that belongs to both triangles. I'll repeat again. Angle BCA equals to angle FCE, and it is equal to alpha. It is a common angle that belongs to both triangles. So we actually proved that the right triangle ABC is similar to the right triangle EFC according to angle similarity rule. We proved that both those two angles are equal to theta, therefore they are equal to each other. Both those two angles are equal to 90 degrees, therefore they are equal to each other. And this is a common angle that belongs to both triangles. So we proved that all the angles of triangle ABC can go into all the angles of triangle EFC. Therefore, triangle ABC is similar to triangle EFC according to angle similarity rule. So we need to write it down. Triangle ABC is similar, this is the sign of similar, to triangle EFD according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we conclude hence AB over AC in triangle ABC equals to EF over EC in triangle EFC. So I will write it down. This will be equation number 1. AB over AC in triangle ABC is equals to EF over FC in triangle EFC. Repeat again. AB over AC in triangle ABC is equal to EF over FC in triangle EFC. Okay? So actually AB, according to equation number 1, AB over AC, AC equals to A plus A, that is to say AC equals to 2A, so we'll substitute AC by 2A. It is equals to EF, EF equals to Y according to our definition, over FC, FC equals to A also according to our definition. So in conclusion, we found out that according to equation number 1, AB over 2A equals to Y over A. Here we have A on both sides of the equation, so A will get cancelled and we're left only with AB over 2 that is equal to Y. We'll multiply this equation by 2 and we'll get that according to equation number 1, AB equals to 2Y. Okay, so we can write here that AB equals to 2Y. In the next step we will prove that the right big triangle, triangle ABC, is similar to the right small triangle, this triangle EDF. So why those two triangles are similar to each other? Triangle ABC is similar to triangle EDF. First of all, those two angles are equal to each other, they are both equal to 90 degrees. So angle ABC of triangle ABC is equal to angle EFD, this angle, and both angles are equal to 90 degrees. I'll repeat again. Angle ABC equals to angle EFD and they are both equal to 90 degrees. In addition, those two angles, they are equal to each other, they are both equal to alpha. So angle ACB in triangle ABC is equal to angle DEF, and both angles they are equal to alpha. I'll repeat again. Angle ACB equals to angle DEF and both angles are equal to alpha. Finally, we have those two angles that they are also equal to each other, they are both equal to theta. So angle BAC in triangle ABC is equal to this angle that is actually angle EDF, and both angles are equal to theta. I repeat again, angle BAC equals to angle EDF, and they are both equal to theta. So we proved that those two angles are equal to each other, they are both equal to theta. Those two angles, they are equal to each other, they are both equal to 90 degrees. And both those two angles, they are also equal to each other, they are both equal to alpha. Therefore, we actually proved that all the angles of triangle ABC can go on to all the angles of triangle EDF, this triangle. Therefore, triangle ABC is similar to triangle EDF according to angle similarity rule. So I will write it down. We actually conclude from it that triangle ABC is similar, this is the sign of similar, to triangle EDF according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will derive that AB over BC in triangle ABC is equal to DF over EF in triangle EDF. I repeat again, from the fact that triangle ABC is similar to triangle EDF, we will conclude that AB over BC in triangle ABC is equal to DF over EF in triangle EDF. So actually, AB equals to 2y, so we'll substitute AB by 2y over BC. BC equals to 6, according to what is given us in the question, so we'll substitute BC by 6. Here DF equals to x, according to our definition, and EF equals to y. So in conclusion, we found out that according to equation number 2, 2y over 6 equals to x over y. Here we will divide both the numerator and the denominator of this side of equation number 2 by 2. And we will get that 2y over 2 is y, and 6 over 2 is 3, and it is equal to x over y. Here we will cross multiply this equation number 2, and we will get that according to equation number 2, y squared equals to 3x. So according to equation number 2, y squared equals to 3x. And if we focus on the right triangle, triangle EDF, according to the Pythagoras theorem, we will get that x squared plus y squared equals to 2 squared. X squared plus y squared equals to 2 squared, that is 4. So in the right triangle, triangle EDF, by Pythagoras theorem, PT is a variation from Pythagoras theorem, x squared plus y squared equals to 4. So here we can substitute y squared in this equation number 3 by 3x, because y squared equals to 3x according to this equation number 2. So we'll do it now, and we'll get that according to equation number 3, x squared plus y squared is 3x, equals to 4. Here we will subtract 4 from this equation number 3, and we will get that according to equation number 3, x squared plus 3x minus 4 equals to 0. So here we have a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for, and we will find out the value of x according to the following formula. X it is equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. So we will put the data inside the formula for x, and we will find out the value of the values of x. So according to this formula, x equals to minus b, b equals to 3, so minus b is minus 3, plus minus square root of b squared. B equals to 3, so b squared is 3 squared, that is 9. Minus 4 times a is 1, c is minus 4, over 2a. A is 2, so 2 times 1 is 2. So in conclusion, we found out that x equals to minus 3 plus minus 4 times minus 4 is plus 16, and 16 plus 9 is 25. So inside the root we have only left with 25 over 2. So actually we got here that according to what we found is that x equals to minus 3 plus minus the square root of 25 is 5 over 2. So here we will have two solutions that are possible for x. The first solution for x, it is actually x1, it is equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8 over 2. Minus 8 over 2 is minus 4. So we found out that x1 equals to minus 4. If x is the length of side DF in the right triangle DEF, so x is a length, so it must be a positive number. X is a length, therefore it must be a positive number. Therefore x can never be equal to minus 4, that is a negative number, so we'll cancel this solution and we're left only with the second solution, x2, that is equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So we found out that x2 equals to 1. In the next step I will copy the right triangle DEF, and we will find out the value of cosine theta. Okay, so in this right triangle EDF, we know that cosine theta, triangle EDF, in this right triangle EDF, cosine theta equals to dF over dE. df equals to x, that is equals to 1, de equals to 2. So in conclusion, we found out that cosine theta equals to 1 over 2. So if cosine theta equals to 1 over 2, it means that theta itself equals to 60 degrees. Okay, we found out that the size of this angle, angle theta that we are looking for, it is equals to 60 degrees. Okay, so we finished with the first method. In the next step, I will present to you how to find out the size of angle theta according to the second method. In the second method, we will define this angle as angle alpha as we did in the first method. We have already found out that alpha equals to 90 degrees minus theta in the first method. And then I will copy the right triangle ABC and we will analyze the right triangle, triangle ABC. But first of all, we'll define AE as A as we did in the first method. Therefore, EC will be also equal to A. Now I'll copy the right triangle ABC. You can see from the drawing that the hypotenuse AC equals to A plus A, that is 2A according to our definition. So I copied the right triangle, triangle ABC in this new page. So in the right triangle, triangle ABC, we know that cosine alpha equals to BC over AC. BC equals to 6 and AC equals to 2A. So here we will divide both the numerator and the denominator of this side of equation number 1 by 2, and we will get that 6 over 2 is 3 and 2A over 2 is A. So in conclusion, we found out that according to equation number 1, cosine alpha equals to 3 over A. Here we will multiply this equation, equation number 1 by A, and then we will divide it by cosine alpha, and we will get that according to equation number 1, A equals to 3 over cosine alpha. Okay? So we found out that according to equation number 1, A equals to 3 over cosine alpha. In the next step, we will focus on the right triangle, triangle DEC or EDC. So I'll copy the right triangle EDC in a new page and we will analyze the right triangle, triangle EDC. So this is the right triangle EDC that I copied from the original drawing. Triangle EDC. In the right triangle, triangle EDC, This will be equation number 2. We know the tangent alpha equals to dE over AC. D equals to 2 according to what is given as the equation, EC equals to 8. So in conclusion, we found out that according to equation number 2, tangent alpha equals to 2 over A but according to equation number 1, we have already found out that A equals to 3 over cosine alpha equals to 3 over cosine alpha, so we can substitute A in equation number 2 by 3 over cosine alpha from equation number 1. We will do it now, we will get that according to equation number 2, tangent alpha equals to 2 over cosine alpha, but cosine 2 over A, but A over, according to equation number 1, equals to 3 over cosine alpha. So we got here the tangent alpha. In conclusion, it is equals to 2 times cosine alpha over 3. And we know that tangent alpha is sinus alpha over cosine alpha, so we substitute tangent alpha by sinus alpha over cosine alpha. We'll do it now. We get that tangent alpha is sinus alpha over cosine alpha, and it is equal to 2 times cosine alpha over 3. Here we will cross multiply this equation, equation number 2, and we get that according to equation number 2, 3 times sinus alpha equals to 2 times cosine square alpha. And we have the trigonometric identity that sinus square alpha plus cosine square alpha equals to 1. Here we subtract sine square alpha from this trigonometric identity, and we'll get that cosine square alpha equals to 1 minus sinus square alpha. That is to say, we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha according to this trigonometric identity. We'll do it now, and we will get that according to equation number 2, 3 sine alpha equals to 2 times cosine square alpha, but cosine square alpha according to this trigonometric identity equals to 1 minus sine square alpha. Here we'll open the brackets, and we'll get that according to equation number 2, 3 sine alpha equals to 2 times 1 is 2, and 2 times 1 sine square alpha equals to minus 2 times sine square alpha. Here we will add 2 sine square alpha to this equation, equation number 2, and we get that according to equation number 2, 2 sine square alpha plus 3 sine alpha equals to 2. Here we subtract 2 from this equation, equation number 2, and we'll get that according to equation number 2, 2 sine square alpha plus 3 sine alpha minus 2 equals to 0. So we have here a quadratic equation. The coefficient A equals to 1, the coefficient B equals to 3, and the coefficient C equals to minus 2. And the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. We'll put the data inside this formula and we'll find out the value of the values of x. So here we have x equals to minus b, b equals to 3, so minus b is minus 3, plus minus square root of b squared, b equals to 3, so b squared is 3 squared, that is 9, minus 4 times a is 1, times c, that is, actually here I made a mistake. As you can see, the coefficient a equals to 2, the coefficient a equals to 2, so it is b squared is 9 and minus 4 times a is 2, so it is times 2, times c is minus 2 over 2a. A is 2, so 2a is 2 times 2, that is 4. So in conclusion, we found out that x equals to minus 3 plus minus square root of minus 4 times 2 is minus 8, and minus 8 times minus 2 is plus 16. 16 plus 9 is 25, so inside the root we have left only with 25 over 4. So here we have x equals to minus 3 plus minus square root of 25 is 5 over 4. So here we have two solutions that are possible for x. The first solution is x actually here we should notice that the variable that we are looking for is sinus alpha, therefore x equals to sinus alpha. Okay, so we substitute x by sinus alpha because the variable that we are looking for, x is sinus alpha actually. This quadratic equation, the variable that we are looking for is sinus alpha, so x equals to sinus alpha. So we get that sinus alpha equals to either minus 3 minus 5 over 4, minus 3 minus 5 is minus 8, and minus 8 over 4 is minus 2. So we found out that sinus alpha equals to minus 2. Sinus alpha equals to minus 2. So, but because of the fact that the function sinus, the range of values that it can accept, the range of values that sinus alpha can accept, they are from minus 1 to plus 1. Sinus alpha can accept values that are ranging from minus 1 plus 1 to minus 1 to plus 1. And minus 2 exceeds this range of values of sinus alpha can accept. Therefore, this solution is the correct solution, or in other words, sinus alpha can never be equal to minus 2. Because the range of values that sinus alpha can accept, they are from minus 1 to plus 1. And minus 2 exceeds this range of values, therefore it is not correct answer. We'll cancel this solution. Sinus alpha can never be equal to minus 2. And we left only in the solution that sinus alpha equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is actually divided by 4, not by 2. So it is divided by 4. Here 2a is 4. So minus 3 plus 5 is 2, and 2 over 4 is 1 over 2. So we found out that sinus alpha equals to 1 over 2. And if sinus alpha equals to 1 over 2, it means that alpha itself equals to 30 degrees. So we found out that alpha equals to 30 degrees. And we have the equation that alpha equals to 90 degrees minus theta. Here we can write down that alpha equals to 90 degrees minus theta. Here we will add theta to this equation. But first of all, we substitute alpha by 30 degrees, and we get that 30 degrees equals to 90 degrees minus theta. Here we will add theta to this equation, and we will subtract 30 degrees, and we will get that angle theta equals to 90 degrees minus 30 degrees. 90 degrees minus 30 degrees is 60 degrees. So we found out that the angle that we are looking for, angle theta, equals to 60 degrees. Okay? This angle theta, the angle that we are looking for, it is equal to 60 degrees. We finished with the second method. In the next step, I will summarize the lecture. We'll start with the first question. So here in the drawing we have a semicircle that is inscribed by a quarter circle. We know that the radius of the quarter circle equals to 3 units, and we want to find out the area of the semicircle that is inscribed by the quarter circle. So we defined the center of the semicircle as point O, and then I presented to you rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have tangent AB that is tangent to this circle at point M is the point of tendency, and we have the radius OM is the radius of the circle, that is to say it is equal to R. And here the radius OM, it is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. So in this case, tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So we can implement rule number 1 in our drawing. From the center of the semicircle, that is to say from point O, we draw the radius OB. The radius OB of this semicircle, that is equal to R, it is drawn to the point of tendency, that is to say it is drawn to point B, that is the point of tendency of tangent AC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent AC will be perpendicular to the radius BO. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees, according to rule number 1. Likewise, we draw the radius OD. Here, we join points OD, so OD is the radius of the semicircle that is equal to R. So here, the radius OD of this semicircle, it is drawn to the point of tendency, that is to say it is drawn to point D, that is the point of tendency of tangent CE with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. So CE is perpendicular to DO. So if CE is perpendicular to DO, that means that this angle equals to 90 degrees and this angle will also equal to 90 degrees. And because of the fact that ACE is a quarter circle, C is the center of the quarter circle, and the angle ACE must be equal to 90 degrees. So in quadrilateral BOCD we have 3 right angles. And the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle that is actually angle BOD. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay, we subtracted 270 degrees from this equation and we found out that the missing angle BOD equals to 360 degrees minus 270 degrees, it is 90 degrees. So this angle BOD, the missing angle equals to 90 degrees. Therefore, in quadrilateral BOCD we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral BOCD as a rectangle. Quadrilateral BOCD is a rectangle. And we have rule number 2, according to rule number 2, that the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of rectangle BOCD are equal to each other. It means that BO must be equal to CD according to rule number 2. BO must be equal to CD according to rule number 2. But we have already found out that BO equals to R. It is the radius of the semicircle. So we can write here that BO equals to R. And from this equation R equals to BO equals to CD, we will derive that CD is also equals to R. Here CD is also equals to R. Likewise, according to rule number 2, we will get that OD equals to BC. OD equals to BC according to rule number 2. But we have already found out that OD equals to R. It is the radius of the semicircle. So here OD equals to R. And from this equation R equals to OD equals to BC, we will derive that BC is also equals to R. Here BC is also equals to R. Therefore, in quadrilateral BOCD, we have 3 equal sides. All its sides are equal to R, and it has also 4 right angles. Therefore, quadrilateral BOCD is not a rectangle but a square. Okay? Quadrilateral BOCD is a square. Then we join points C and O together by a straight line. CO is the diagonal of square BOCD. In order to find out the length of diagonal CO of square BOCD, we implemented the Pythagoras theorem on the right green triangle, triangle COD. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CO square equals to OD square plus CD square. So CO square equals to OD square, OD equals to R, so OD square is R square. OD square is R square, and CD equals also to R, so CD square, it is equal to R square. So in conclusion, we found out that CO square equals to R square plus R square. R square plus R square is 2R square. So in conclusion, we found out that CO square equals to 2R square. We took a root out of this equation and found out that CO equals to the square root of 2 times R. So the length of diagonal CO, it is equal to square root of 2 times R, that is the radius of the semicircle. In the next step, we extended diagonal CO until, by a straight line, until it touches the quarter circle at this point S. Okay, point S is the touching point of the extended CO and the quarter circle. And then we found out the length of the small line segment OS. What is the length of the small line segment OS? From the drawing, it is very easy to see that the length of line segment OS equals to SC minus OC. Again, SC minus OC equals to the length of the small line segment OS. SC is the radius of the quarter circle. Why? Because it starts from the center of the quarter circle, that is to say from point C, and ends at point S, that is a point on the quarter circle itself. And this is exactly the definition of a radius. That is to say SC is the radius of the quarter circle, that is equal to 3 units. So SC equals to 3 units. We have already found out that CO equals to square root of 2R. Therefore, SO will be equal to SC minus OC, that is 3 minus square root of 2R. So we found out that the length of the small line segment OS equals to 3 minus square root of 2R. Then we completed the quarter circle to a circle, and then we extended diagonal CO by a straight line until it touches the circle at this point, point M. What is the length of line segment CM? C is the center of the circle, and M is the point on the circle itself. This is exactly the definition of a radius. And the radius of this circle equals to the radius of the quarter circle. This is 3. So MC equals to 3. Then I presented to you rule number 3. According to rule number 3, if chord AB intersects with chord CD at point O is the intersection point, then AO times OB equals to CO times OD. Okay, so we can implement rule number 3 in our drawing, because in our drawing we have chord SM that intersects with chord GF at point O. Point O is the intersection point of chord SM with chord GF. Therefore, according to rule number 3, we will get that MO times OS equals to GO times OF. Again, I will repeat again that chord SM intersects with chord GE at point O. Point O is the intersection point of chord SM with chord GF. Therefore, according to rule number 3, we will get that MO times OS equals to GO times OF. What is the length of MO? MO equals to MC plus CO. Again, MO equals to MC plus CO. We have already found out that the length of the small line segment OS is 3 minus square root of 2R. GO equals to R, it is the radius of the semicircle. OF, it is also equals to R. Why? Because it starts from the center of the semicircle, and then the point F, that is the point of the semicircle itself. And this is exactly the definition of a radius. So GO equals to OF, and both the radiuses, the radii of the quarter of this semicircle. Okay. So GO equals to R and OF also equals to R. Therefore, R times R is R squared. MC equals to 3. CO equals to square root of 2R. So MC plus CO equals to 3 plus square root of 2R times OS, that is 3 minus square root of 2R, equals to R squared. This expression, 3 plus square root of 2R times 3 minus square root of 2R, it is very similar to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. And here, in our specific expression, A equals to 3 and B equals to square root of 2R, so this expression must be equal to A squared minus B squared according to this trigonometric algebraic identity. A equals to 3, so A squared is 3 squared, that is 9. B equals to square root of 2R. So B squared is square root of 2R squared, that is actually 2R squared. So in conclusion, we found out that 3 plus square root of 2R times 3 minus square root of 2R equals to 9 minus 2R squared. And it is equals also to R squared. We added 2R squared to this equation, and we found out that 9 equals to 3R squared, because 2R squared plus R squared is 3R squared. We divided by 3 this equation. 3R squared over 3 is R squared, and 9 over 3 is 3. 9 over 3 is 3, so in conclusion we found out that R squared equals to 3, and the area of the semicircle equals to pi R squared over 2. R squared is 3, so we substitute R squared by 3. So in conclusion, we found out that the area of the semicircle equals to either 3 pi over 2 square units or in terms of numbers, it is equal to 4.71 square units. We finished with the first method, then I presented to you how to find out the area of the semicircle according to the second method. In the second method, we used all the things that we have already found out in the first method. We have already found out that BOCD is a square. The diagonal of square BOCD equals to square root of 2 times r, that is to say diagonal CO equals to square root of 2 times r, and all of its sides of the square are equal to r, the radius of the semicircle. Then we already found out that GO equals to r and OF also equals to r, that is the radius of the semicircle. Then we join points C and F together by a straight line. C is the center of the quarter circle. F is the point of the quarter circle itself. Therefore, CF is the radius of the quarter circle, that is equal to 3 units. For the same reason, CG is also the radius of the quarter circle, that is to say it is equal to 3 units. So we created here isosceles triangle CGF. And I copied the isosceles triangle CGF in a new page, and we analyze the isosceles triangle CFG. First of all, triangle CFG is an isosceles triangle because side CF equals to side CG. And whenever you have two sides that are equal to each other in a triangle, it is defined as isosceles triangle. And because of the fact that those two sides are equal to each other, FG must be the base of the isosceles triangle CFG. So FG is the base of the isosceles triangle CFG, and CO, that is equal to square root of 2 times r, is the median to the base. Why CO is the median to the base? Because of the fact that CO bisects the base FG into two equal parts. That is to say FO equals to OG equals to R. For that reason, CO is the median to the base FG. And we have rule number 4 that says that the median to the base in an isosceles triangle is perpendicular to the base. So the median CO to the base FG in the isosceles triangle CFG is perpendicular to the base. That is to say CO is perpendicular to FG. That is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees according to rule number 4. Again, because of the fact that according to rule number 4, CO is perpendicular to FG, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees according to rule number 4. So I copied this right triangle COG in a new page, and we implemented the Pythagoras theorem in this right triangle COG. This is the right triangle COG. CO, it is the diagonal of the square that is equal to square root of 2r. OG is the radius of the semicircle that is equal to r. And CG is the radius of the quarter circle that is equal to 3 units according to what is given us the question. So here, according to the Pythagoras theorem, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. That is to say CG square equals to CO square plus OG square. CG equals to 3, so CG square is 3 squared, that is 9. CO equals to square root of 2r, so CO square is square root of 2r squared, that is 2r squared. OG equals to r, so OG squared is r squared. So in conclusion, we found out that 9 equals to 2r squared plus r squared. 2r squared plus r squared is 3r squared, so we found out that 9 equals to 3r squared. We divided this equation by 3 and we got that r squared equals to 3. 9 over 3 is 3. And the area of the semicircle equals to pi r squared over 2. R squared equals to 3, so we can substitute r squared in this equation by 3. We did it, and we got that the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equals to 4.71 square units. We finished with the first question. In the next step, I will present to you the second question. how we solve the second question in two different methods. So here we have the right triangle ABC. You know that angle ABC equals to 90 degrees. DE, line segment DE equals to 2 units, and DE is also perpendicular to the hypotenuse AC, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. We know that side BC of the right triangle ABC equals to 6 units, and we also know that AE equals to EC, and we want to find out the size of this angle BAC that is equal to theta. So in order to find out the size of angle theta, we made a construction from point E, we drew perpendicular on BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. And we defined the touching point of the perpendicular from point E and BC as F. Then we defined this angle as angle alpha, but because of the fact that in the right triangle ABC this angle equals to 90 degrees and this angle equals to theta, this angle must be equal to 90 degrees minus theta. So according to our definition, this angle equals to alpha. And according to what we have already found out just right now, this angle must be also equal to 90 degrees minus theta. So from it we can derive that alpha equals to 90 degrees minus theta. So here alpha equals to 90 degrees minus theta. We added theta to this equation and we subtracted alpha, and we got that theta equals to 90 degrees minus alpha. Okay, and then in this right triangle EFC, this angle equals to alpha, this angle equals to 90 degrees, this angle must be equal to 90 degrees minus alpha. In order to complete the sum of the angles in this right small triangle, 280 degrees, this angle must be equal to 90 degrees minus alpha. But 90 degrees minus alpha equals to theta. So we can write down here that 90 degrees minus alpha equals to theta, according to this equation. Then we found out the value of this angle DEF. The value of angle DEF equals to angle DEC minus angle FEC. Again, DEC minus angle FEC equals to this angle DEF. Again, angle DEF equals to angle DEC minus angle FEC. So angle DEF equals to angle DEC, that is 90 degrees, according to what is given as the question, minus angle FEC. But angle FEC, we already found out that is equal to 90 degrees minus alpha, so we can substitute angle FEC by 90 degrees minus alpha. So in conclusion, we found out, we opened the brackets here, and found out that the missing angle DEF equals to 90 degrees minus 90 degrees, that is 0, minus and minus is plus. So in conclusion, we found out that the missing angle DEF equals to alpha. So if this angle equals to alpha, this angle equals to 90 degrees, this angle must be equal to 90 degrees minus alpha. But because of the fact that 90 degrees minus alpha equals to theta, we can substitute 90 degrees minus alpha here by theta. We did it, therefore we define this angle as angle theta. Then we proved that the right big triangle ABC is similar to the right small triangle FEC. But before that we defined DF as X, EF as Y, and AE as A. And if AE equals to A, EC must be also equals to A, because of the fact that AE equals to EC. So why those two right triangles are similar to each other? Triangle ABC is similar to this triangle FEC. First of all, those two angles are equal to 90 degrees. Therefore, they are equal to each other. In addition, those two angles are equal to each other, they are both equal to theta. And finally, this angle is a common angle that belongs to both triangles, therefore this angle equals to itself. So we actually proved that the right triangle, all the angles of the right triangle ABC can go into all the angles of the right triangle EFC. Therefore, those two right triangles can go are similar to each other according to angle similarity rule. Okay, triangle ABC is similar to triangle EDF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, triangle ABC is similar to triangle FEC, we will derive that AB over AC equals to FE over AC. Again, according to equation number 1, AB over AC equals to EF over FC. So AB over AC, AC is A plus A, that is 2A, so we substitute the AC by 2A. EF equals to Y, FC equals to A. So in conclusion, we found out that AB over 2A equals to Y over A. Here we have A on both sides of the equation, so A will get cancelled, and we left only with AB over 2, that is equal to Y. We multiplied this equation by 2 and found out that AB equals to 2Y. So here we can write down that AB equals to 2Y. Then we proved that the right big triangle ABC is similar to the right small triangle, triangle EFD. Why those two right triangles are similar to each other? First of all, those two angles, they are equal to each other, they are both equal to 90 degrees. In addition, those two angles, they are equal to each other, they are both equal to alpha. And finally, those two angles, they are also equal to each other, they are both equal to theta. So we found out that all the angles of triangle ABC can correspond correspondingly to all the angles of triangle DEF. Therefore, triangle ABC is similar to triangle DEF according to angle similarity rule. Triangle ABC is similar to triangle DEF according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will conclude that AB over BC equals to DF over FE. Again, AB over BC equals to DF over EF. AB over BC equals to DF over EF, okay? So, AB equals to 2Y. BC equals to 2A. AB equals to 2Y, BC equals not to 2A, but BC equals to 6, according to what is given as the question. So we substituted BC by 6. DF equals to X according to our definition, and EF equals to Y also according to our definition. So in conclusion, we found out that 2Y over 6 equals to X over Y. Here we divided both the numerator and the denominator of this side of equation number 2 by 2, and we got that 2Y over 2 is Y, and 6 over 2 is 3. So in conclusion, we found out that Y over 3 equals to X over Y. Because multiplying this equation, equation number 2, we found out that Y squared equals to 3X. So according to equation number 2, Y squared equals to 3X. And if we focus on this right triangle, triangle DEF, it's very easy to see from that according to the Pythagoras theorem, x squared plus y squared equals to 2 squared. Okay, according to equation number 3, x squared plus y squared equals to 2 squared, that is 4. So we can substitute y squared in this equation number 3 by 3x, because y squared equals to 3x according to equation number 2. We did it and we got that according to equation number 3, x squared plus y squared, that is 3x, equals to 4. We subtracted 4 from this equation, equation number 3, and we got that x squared plus 3x minus 4 equals to 0. This is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. A, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. So we'll put the data inside the formula for x, and we'll find out the value of x. So here x equals to minus b, b equals to 3, so minus b is minus 3, plus minus square root of b squared. B is 3, so b squared is 9, minus 4 times a is 1, and c is minus 4. Divided by 2a. A is 1, so 2 times 1 is 2. And inside the root we have minus 4 times minus 4 is plus 16, and 16 plus 9 is 25. So in conclusion, we found out that x equals to minus 3 plus minus 25 over 2. The square root of 25 is 5. So in conclusion, we found out that x equals to minus 3 plus minus 5 over 2. So here we will have two solutions that are possible for x. The first solution for x is x1 equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8, and minus 8 over 2 is minus 4. So we found out that x1 equals to minus 4. but because of the fact that x is the length of side DF of the right triangle DEF, x must be a positive number. X cannot be equal to minus 4, that is a negative number, so we cancel this solution and we're left only with the second solution, that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2 and 2 over 2 is 1. So we found out that x2 equals to 1. So I copied the right triangle EDF in a new page and we actually found out the cosine theta of this right triangle EDF. Here we know that df equals to x, that is equals to 1. D equals to 2, it is given as the equation. This is angle theta. So here cosine theta in the right triangle EDF equals to df over EF. df cosine theta equals to df over ed. Here cosine theta equals to df over ed or de. So cosine theta equals to df, that is 1, over de, that is 2. So in conclusion, we found out that cosine theta equals to 1 over 2, and if cosine theta equals to 1 over 2, it means that theta itself equals to 60 degrees. Here, the size of this angle theta, the angle that we are looking for, is equal to 60 degrees. In the next step, I will present to you how we found out the size of angle theta according to the second method. In the second method, we define this angle as alpha, and as we did in the first method, we know that alpha equals to 90 degrees minus theta. A equals to A according to our definition. EC will be also equal to A according to our definition. So I copied the right triangle ABC in a new page. This is the right triangle ABC. We know that cosine alpha equals to BC over AC. Cosine alpha equals to BC over AC. BC equals to 6 units according to what is given as the question. AC equals to A plus A according to our definition. So AC equals to 2A. So in conclusion, we found out that cosine alpha equals to 6 over 2A. We divided both the numerator and the denominator of this side of equation number 1 by 2, and we got that 6 over 2 is 3 and 2A over 2 is A. So in conclusion, we found out that cosine alpha equals to 3 over A. We multiplied this equation number 1 by A, and then we divide it by cosine alpha, and we got that A equals to 3 over cosine alpha according to equation number 1. Then we focused on the right triangle EDF, and on the right triangle EDC, this right triangle EDC. I copied the right triangle EDC in a new page. Here we have the right triangle EDC that I copied from the original drawing. Here, tangent theta equals to DE over EC. Tangent theta equals to DE over EC. DE equals to 2. EC equals to A. So in conclusion, we found out that tangent alpha according to equation number 2 equals to 2 over A, but tangent alpha equals to 2 over A according to equation number 2. But we have already found out that according to equation number 1, A equals to 3 over cosine alpha. So we can substitute A in this equation number 2 by 3 over cosine alpha. We did it, and we got that tangent alpha equals to 2 over 3 over cosine alpha. That is to say tangent alpha equals to 2 cosine alpha over 3. We substituted tangent alpha by sinus alpha over cosine alpha, and it is equal to cosine 2 cosine alpha over 3. We cross multiplied this equation number 2, and found out that 3 times sinus alpha equals to 2 times cosine square alpha. We have the trigonometric identity that sine square alpha plus cosine square alpha equals to 1. We subtracted sine square alpha from this trigonometric identity, and we found out that cosine square alpha equals to 1 minus sine square alpha. Now we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha. We did it, and we got that 3 sine alpha equals to 2, and cosine square alpha equals to 1 minus sine square alpha according to the trigonometric identity. We open the brackets here, and we got that 3 times sine alpha equals to 2 times 1 is 2, and 2 times minus sine square alpha equals to minus 2 sine square alpha. we added 2 sine square alpha to this equation number 2, and we got that 2 sine square alpha plus 3 sine alpha equals to 2. We subtracted 2 from this equation number 2, and we got that according to equation number 2, 2 sine square alpha plus 3 sine alpha minus 2 equals to 0. So here we have a quadratic equation. In this quadratic equation, the coefficient a equals to 2, the coefficient b equals to 3, and the coefficient c equals to minus 2. And the solution for this quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. The missing variable here, x, is sinus alpha, so x equals to sinus alpha. So here it is actually sinus alpha that is equals to minus x equals to minus b equals to 3, so minus b is minus 3 plus minus b squared, b equals to 3, so b squared is 3 squared, that is 9. Minus 4 times a is 2, and c is minus 2, so it is minus 4 times 2 minus 2 over 2a, a is 2, so 2a is 2 times 2, that is 4. So here we found out that x equals to minus 3 plus minus 4 times 2 is minus 8, and minus 8 times minus 2 is plus 16, 16 plus 9 is 25. So in conclusion, we found out that inside the root we have only 25, that is what is left. So here we have x equals to minus 3 plus minus square root of 25 over 4. The square root of 25 is 5, so in conclusion we found out that x equals to minus 3 plus minus 5 over 4. But we have already said that the missing variable here is sinus alpha, so x equals to sinus alpha, okay? So we can substitute x by sinus alpha because the missing variable here is sinus alpha, so x equals to sinus alpha. So we substituted x by sinus alpha. So here sinus alpha, we have two solutions that are possible for sinus alpha. The first solution for sinus alpha is that sinus alpha equals to minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8, and minus 8 over 4 is minus 2. So we found out that sinus alpha equals to minus 2, but because of the fact that the range of values that function alpha can accept, they are ranging from minus 1 to plus 1, that's all. And minus 2 exceeds this range. That is to say, sinus alpha can never be equal to minus 2. Therefore, this solution, that sinus alpha equals to minus 2, is an incorrect solution. We cancel the solution, and we left only with the second solution, that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 over 2. So if sinus alpha equals to 1 over 2, it means that alpha itself equals to 30 degrees. And we have already found out that alpha equals to 90 degrees minus theta, so we can write here that alpha equals to 90 degrees minus theta. And because of the fact that alpha equals to 30 degrees, we can substitute alpha by 30 degrees. We did it, and we got that 30 degrees equals to 90 degrees minus theta. Here we added theta to this equation, and we subtracted 30 degrees, and we found out that angle theta, the angle that we are looking for, equals to 90 degrees minus 30 degrees, that is 60 degrees. That is to say, we found out that the angle, the missing angle, the angle that we are looking for, theta, it is equal to 90 degrees according to the second method also. Okay, thank you very much.